How's it going, everybody? So last episode, we kind of performed a miracle, if you will. We performed some alchemy. We said, we're going to take the empty set, right, and build the entire real number line. And we did this first with the von Neumann hierarchy, right? We defined the natural numbers in this way. And then we used the natural numbers to give us, we did a really clever thing with sets to describe the differences in the ordered sets or whatever to give us, or construct the integers. And then again, we created an ordered field of rational numbers, but guess what? Rational numbers have holes in them, so we use the Dedekind cuts to give us the real number line. And we define real numbers in terms of the Dedekind cuts, okay? It's complete, it's a dense set with no holes, right? But, and again, that's kind of a lot. I think most of that was in the last 15 minutes of the video, so before we you move on to watching this video, I would recommend going back to that one, just the last 15 minutes, watching through that. The mic quality is a little bit raunchy, but hopefully it's okay. But, if you look at closely what we've constructed, right, the set of real numbers, it's dead, okay? And what I mean by that is, if we have some point like 0, right, and then 1 on the real numbers, we really have no mechanism to move between 0 and 1, right? It's a frozen kind of like crystal, if you will. I guess that's the way that I'm describing it. It's a continuum. It's a frozen continuum. There's no idea of speed. There's no idea of approaching. There's no change, right? And if we stop now, we will have a universe, or even we will have a language to describe the universe with only static nouns, okay? We don't have any verbs, in other words. Remember, we constructed mathematics with ontology, epistemology, and logic, right? This was our grammar of truth, our objects, and our method of knowing things. But if we want to describe a planet, right, orbiting a star, or some kind of, stock price fluctuating, we need to animate this continuum. And so this is why I'm calling it continuum analysis. This isn't anything particularly novel, but what it does is it kind of tries to synthesize all of these topics. If you've seen them before, it's great. If you haven't, I'm going to try my best to animate this and to explain this in a way that's a little more imaginative and that connects everything from, scalar calculus, right? To metric and topological spaces, differentiation as a linear map, complex analysis, Lebesgue theory, measure theory, and probability, okay? All of this is going to be the animation of the real numbers, if that makes sense, all right? But what's stopping us from doing this? And what has stopped us from doing this for a really long time, about like more like 1,500 years, but for around 2,000 years-ish, mathematics was paralyzed by something called Zeno's paradoxes. And you've probably thought of this idea when you were a kid. I know when I was like 5 years old, I kind of thought of this idea and I debated this. Most people have these thoughts, which is if you want to move from a point, right, A to B, right, and you're like, you're looking at the sidewalk or something, the way to think about this is you have to pass the midpoint, right, between A and B. You're going to go halfway to A and B. But to pass that midpoint, you also have to pass halfway between where you're at point A and the midpoint. So that's like called a quarter point. So to move at all, you have to basically traverse an infinite number of points, right, in a finite amount of time. And logically, that kind of doesn't make any sense, right? I mean, like of course, when you experience it, right, we go through it every day, and we're like, yeah, things move, whatever. But logic says that's impossible, right? If you assume that you're going from a point to another point, and there's a halfway between it, So for centuries, right, we tried to fix this idea with infinitesimals, and this is what Newton and Gottfried Leibniz kind of inherited from the Arabics, right? And from the Arabic method of doing math, or of constructing mathematics. They were the ones that originally came up with the idea of infinitesimals. And these were like ghostly numbers that were just kind of smaller than anything else, but not zero, okay? And they worked to calculate things and to create calculus and all of this, but they were logically incoherent, okay? And infinitesimals are really incoherent, okay? When we hand wave this during calculus, like, yeah, you know, this is a little dx, right? Or even if you look at a 3 blue, 1 brown video, you'll see it's a little infinitesimal. There's like a small nudge. It's a little better, but I mean, then again, it's still vague, right? It's a vague intuition of movement, right? So what we need is something better. We need to define it with logic. And this is how we're going to breathe life into the continuum. But first, before we get on to that, I need a drink because this is going to be a long episode, and I hope to cover all of these things in a way that's digestible. I'll be right back. All right, what's up? So how do we define approaching without using time? We typically say, right, as x gets closer to, you know, a, right, f of x gets closer to L or something. But like, you know, gets closer implies time, right? So what we need to do, remember, mathematics is timeless, right? We aren't assuming anything about time. So, you know, we have a continuum that exists. It's complete. It's Archimedean, built from Dedekind cuts, or you can also use something called Cauchy sequences. We didn't cover this, but that's another approach. Pick up a real analysis book. You'll see what that is. It's not hard. But, you know, given it remains frozen, and, you know, and by the way, Dedekind cuts came first, okay? But no function changes really in a controlled way. So if we want to describe change, we need to define what it means for something to approach. Of course, I wrote all of that out. And we can use Cauchy's, or the language of limits, and Weierstrass as well. You know, he perfected it in the 1870s. Really, every later concept that comes later comes from this foundation. All right. So let's construct this. Let's construct this idea or this definition of a limit. And actually, deeply, the best, most intuitive way to think about delta epsilon, or to think about this idea of a limit, is to turn it into a game. So what it is a challenge response game between two players, an adversary and a prover. This is the epsilon-delta definition, okay? Here's the game. You claim the limit. First of all, what you have to do is claim that a limit is L, okay? So you claim that you know the limit. The adversary, or the skeptic, will first choose. He doesn't believe you, right? They're going to give you an error tolerance, epsilon, error, okay? And they say, I want the output to be within this tiny window of the target, okay? In order to believe you that it's L. That's fundamentally what's happening. And your job as the prover is to find a precision radius delta, and you're going to say, fine, Mr. Adversary, fine. If you input any number within this delta distance of the target, the output guarantees your epsilon error. And if you can win this game for any epsilon, the adversary throws at you, no matter how microscopically small, then the limit exists. And then the question becomes, how do I know that I won, basically, right? And the idea, first of all, is to recognize that we haven't described motion. We've described a static relationship of arbitrary closeness. Arbitrary closeness, or arbitrarily close, choosing some configuration space of possible, errors and being able to choose from that, and is a very, very important line of reasoning, and it is extremely physical. This is a physical line of reasoning. If you've ever seen the variational calculus and how it's derived, we use arbitrary paths. Okay, that's getting ahead of myself, but I just want to show you why this is really, this game here that we're playing is physical, right? And it rests on some metaphysical assumptions. So we have replaced essentially, again, infinitesimals with something that's called arbitrary closeness. And this actually solves Zeno's paradox. We don't have to count infinite steps. We just have to satisfy some inequality. All right. So what this looks like in practice is, if we want to find the limit of a sequence, this is a sequence. We'll define it as a function from the natural numbers to the real numbers, and we'll denote it as x sub n. A sequence converges to L if there exists some some epsilon greater than 0. For all epsilon greater than 0, there exists some natural number, okay, some chosen natural number out of the set of all natural numbers, such that for all natural numbers greater than that chosen little natural number, that the distance, if you will, let's define it as the distance first, that the distance of that sequence, right, subtracting off that limit that we said it converges to, is less than the error tolerance, okay? So let's look at the harmonic sequence. Our claim is that as n goes to infinity, 1 over n goes to 0, okay? First, we want to prove this. So first, the adversary is going to provide to you, hey, this is some error epsilon that's greater than 0 that we're going to tolerate, okay? And what we need to do is prove that 1 over n minus 0 is less than epsilon, which simplifies to 1 over n is less than epsilon. This means that n is greater than 1 over epsilon. If we choose some number, okay, that belongs to the natural numbers, and we take the ceiling of 1 over epsilon plus 1, we, again, going back to the chain of knowledge to use different properties or proofs, etc., what we can do is say the Archimedean property guarantees that such an integer exists. And if we want to verify that, we say for any n that's greater than that chosen natural number that we picked out of the natural number, out of the set of all natural numbers, the limit is 0, right? And we've shown this, okay, that it doesn't matter what we choose, because as long as we choose the n that's greater than this reference natural number, this is always going to be less than that error tolerance. And we have then proven the limit. All right? Does that make sense? And we can do the same thing for divergence by oscillation. So let's take a sequence, -1 to the n, and we're going to show that it actually doesn't converge. So to prove that something does not converge, again, we can use our epistemological framework, right? So we first choose, the adversary will choose epsilon equals 1, okay? And in the universe, assume that it converges to some limit, and we must provide n such that for all n that's greater than that chosen n, that reference n, that the distance is less than 1, okay? We need to prove that. And if you pick an even number, and then you pick an odd number for both of those cases, if we apply the triangle inequality, which is basically a property of all triangles, both of the legs, the sum of them has to be less than or equal to the hypotenuse. Okay, that's what that means. And if we do a triangle inequality for the distance between -1 and 1, what we'll get is that 2 is less than 2, which is false. So that means we can fundamentally know that no such limit actually exists, okay, for that sequence. This is great, okay, because we're now using everything that we had previously to try to say things about limits, okay, or just essentially real numbers, okay, and how they behave and how they move, all right? And so we have our first divergence by oscillation. Well, let's look at the limit of a function. And remember, functions are just sets, right, on a graph in a Cartesian or a product of two sets, okay? So let's look at the limit as x goes to a of f of x is equal to L. And we can just define it using the same thing. So we'll say for all epsilon greater than 0, there exists some delta such that, again, the distance between x and a is less than delta, which then, if this is true, then this implies materially that the distance between the function of x minus the value at L where x, for the limit, right, as x goes to a, well, f of x minus L is less than epsilon. And we can show that. Let's look at a quadratic function. So let's say the claim here is that this limit will approach 5, all right? And of course, as if you could verify this, this is this is very intuitive, right? If you just plug in the number. But we want to show that the limit exists. This is what we're doing now. We're moving. So what we're doing is showing movement without having to actually move anything, right? We're just using inequalities to show that it's always true, basically showing that the limit exists. So what happens is we can actually reverse engineer this claim. In fact, this is another method that we can use to prove. So let's say we want that this minus 5 is less than epsilon. And this is really just directly showing this. So if we factor out this, we can control that the distance between x and minus 2 with delta. And we must bound something called the nuisance factor, okay? And this is really what's happening here. We want to bound this 3x plus 2. And we want to assume first, let's just assume that delta is less than 1, okay, less than or equal to 1. Then if we take the distance between x minus 2 is less than 1, this implies, right, that x is, this implies that x is between 1 and 3. And in this range, this nuisance term is maximized at x, of course, at x equals 3. So we can then show this here, that when we plug it in at 3, it equals 11. Choose delta to be the minimum of 1 comma epsilon over 11. And if, 0 and delta bound the distance between x and minus 2, we can then make this equivalent to epsilon itself, okay? And that shows, again, that this statement here, this claim, is true. We proved it by just simply directly substituting it into the limit and finding some delta that makes it possible, right? Also, we can also show non-existence, again, for functions, okay? And we can construct two sequences. One method that's really popular when handling some of these weirder functions is constructing sequences that approach 0 or approaching 0 that yield different values. And then when you compute them, you can then get the contradiction, right? 0 is not equal to 1, right? Or you can get two different values here for the sequences, if that makes sense, okay? So the function can't approach a single value L, therefore we can prove that it's non-existent. We're going to find something else called continuity. Continuity at a point, we would say f is continuous at a point if this limit is satisfied, or equivalently the verbose official limit, okay? But instead we would substitute it as f of a, where f of a is that limit itself, okay? So let's look at, again, if we claim that these functions here are continuous at x equals 0, we can then find the inequalities and choose delta to equal epsilon here. And the size of x, if it's less than delta, then the size of the function itself would be less than or equal to x, which is less than epsilon, okay? And you can show that very nicely. Let's also define uniform continuity. F is uniformly continuous on a set S if delta works for all points S simultaneously, okay? So now we can replace this, instead of a single continuity at a point, we can just say continuity for a whole set, okay? Continuous on an entire set of outcomes and just generalize this. As you can see, we always start from specific examples, right? We start from specific things and try to look for generality. That's the whole development of mathematics. It's the whole idea of constructing these things. All right, and so we're going to bound this again for epsilon, and you can look again. We can show that this is actually failure. This has a failure of uniformity. We don't have uniform continuity of x squared is not uniformly continuous on all the real numbers. The reason why, think about this, if we're taking the set, right, on all real numbers, the slope is getting really, really steep for x goes as it tends to infinity or negative infinity, okay? And again, we're trying to keep the output change within some error tolerance. And if the input change must get smaller and smaller, so there's no universal delta. Okay, that's the kind of idea. And you can prove this. You can pause the video and work through that if you want. And there's also, this is successful if we have a compact set, which basically means that we have some negative 10 to 10 interval that we are looking at. And what this does is we can actually define some delta then that works, right? Delta epsilon over 20. This works for any x and y in the domain. So we would say that on a finite interval, this function is uniformly continuous. All right. Let's define something else. This is what we call differentiability. And what this basically means is motion is not just some position. It's actually the rate of change of some position on the real number line, okay? So we'll say f is differentiable at a with derivative L, okay? L is the limit, okay? The derivative is a limit here, and it is denoted as f prime of a if we say some f of a plus some thing that is arbitrarily close, h, right, minus f of a is equal to some limit, okay? If that limit is defined for this difference here. A better way to approach this is say equivalently, there exists a number, L, right, that is the derivative, such that we have it as a line, okay? This becomes a linear form, or a way to approximate the derivative itself. And this becomes really important for multivariable calculus, okay? Because when you look at this definition, and we have L up here is equal to 0, that's the equation of a line, all right? Or it becomes a map, a linear map. So this is just a better, I think it should be always, introduced like this. Hey, the definition of the derivative is limit, but also you can rearrange it as such and get an equation that's satisfied in this way. Next, we will look at the parabola again, and we can really just compute this via the definition of the limit and just simplify it algebraically. It's straightforward. An interesting case is the derivative happens to not exist for f is equal to the absolute value of x at some reference point a is equal to 0. The right limit is 1 and the left limit is -1, right? It's tending to -1. For the definition of the derivative. So 1 is not equal to -1, so it's not differentiable, okay? So this is a problem, right? Because, if we can't define the derivative at a point, or, it becomes kind of a nuisance, in other words. But let's look at what does the derivative allow us to do? It allows us to construct some really important theorems. We'll say if the function on a finite interval mapping to the real numbers is continuous in general, and if the function at a point is less than 0, which is less than f of b, then there exists some, okay, and what this is saying is it's ordering in such a way that this is negative and this is positive. Then there exists some c, okay, that exists on the interval between a and b, such that the function itself is equal to 0. Okay, that just means, think about it. This is actually a really simple statement, but it's called the intermediate value theorem because this allows us to encode properties of the derivatives and continuity and limits. Okay, so think about a graph, right? You have some negative part and then some positive part, and you're drawing the line between them, right? Assuming it's continuous, right? If the function is not continuous, then this doesn't have to be true. But if it is continuous, it is necessary that there exists a 0 of that function that intersects the x-axis, okay? Or that intersects that. So we'll say, in order to prove that, what we can do is we can say the set is equal to, we'll just define some set that if we have some something within the interval from a to b, such that f of x is greater than or equal to 0, okay? That is the set of everything. And the set is non-empty, and A is an S, and it's bounded by B to be its upper bound, right? Remember? Because that's how we're defining it. By the completeness axiom, we assume that C is in, or that C equals the supremum of S, and that it exists, okay? By the axiom. We depend on that axiom directly. So then that means that continuity implies that F is positive in something called small neighborhood. Again, I just clicked on this on accident, but we're defining a small neighborhood, which means we're finding C is, we're subtracting off C by that delta that we chose. And this contradicts C being the least upper bound of negative values, okay? And if C is greater than 0, continuity implies that F is negative, okay? In C plus delta, and this contradicts C being an upper bound since there are negative values to the right. Therefore, we can hence conclude that f of C must equal 0, okay? So this is the only possible outcome that respects this axiom. And so the intermediate value theorem is, it seems like a really obvious result, and it's pretty intuitive, but the proof mechanism is interesting because we have to rely on the idea of completeness, right? So that's what completeness means, okay? Or that's how completeness can be used to help us create really important theorems that we can use later when we construct more involved pieces or more involved mathematics. The next theorem is called the extreme value theorem, and this one's a little easier to understand, but continuous f on closed bounded interval here attains a maximum and a minimum, okay? Boundedness, okay? So if f were unbounded, we could find a sequence, and the Balonzo-Weierstrass, I think it's from his 1930-ish paper, or sorry, his 1870-ish paper, can't remember, but he shows, that's their theorem there, or their relation that they showed. X sub n has a subsequence converging to x, and by continuity, f of x must be finite, and we get a contradiction, okay, which then can give us the proof that we need to know the boundedness, right? So suppose the universe was unbounded, we can find a sequence, etc., and find the contradiction. Next is attainment. So let's let m be the supremum of the function on that interval. If you pick a sequence such that it converges to the supremum, then the subsequence argument forces the limit point C such that f of C is equal to m. All right, so that's the extreme value theorem. There's also a uniform continuity theorem. Continuous f on a compact interval is uniformly continuous. You can argue this by contradiction. Again, this is just another theorem. Another theorem that you get is an instance of algebra. So let's say the function f of x approaches L, and let's say g of x approaches m, then f times g of x just gives you the product of both their limits, all right? And there's a way to prove it. There you go. So what we have now is that we have a language where continuous change is properly expressed, and we no longer have a frozen real line, but now we have some mathematical kind of technology to traverse real numbers with control. And the delta epsilon, or the epsilon delta definition, really allows us to philosophically resolve Zeno's paradoxes as well with some physical reasoning. Okay, that's really important. If we replace the impossible idea of moving through infinite points in a mathematical way with static, rigorous logic of inequalities, Zeno's paradoxes would just, destroy the universe. So again, This kind of is, I guess, narrating the cult that I'm trying to make, that, you know, physics and metaphysics are more fundamental than mathematics. But then again, please challenge me on this, and maybe I'm making some assumptions that, or maybe I'm making some mistakes as well. So feel free to debate me on this in the Discord server. All right. Hold up, I need a drink. Okay. Metric and topological spaces. So I want you to notice something about the epsilon-delta language. Essentially, again, how I explained it, the most intuitive way to understand it is that it's a game, right? You have an adversary and you're trying to prove something about some set limit, all right? And you're finding the delta. We played it using the absolute value, okay? We were measuring distance between them with some kind of implied ruler. And this is a little bit of a logical jump, but what if we don't have a ruler to measure the distance between them? What if we're working on some weird like curved shape or network, right, or graph or something like that, where distance really isn't defined or makes any sense? In the early 20th century, we realized here that distance is a luxury. We don't actually need to know how far apart things are. We only need to know what is near, okay, or what is near what, basically. This is the idea of topology. What we do is we strip away the metric, the distance function, and we are left with something we call the open set, okay? And think of an open set as like a safety bubble. If a point is in an open set, it has a little buffer zone around it, entirely contained in the set. And by doing this, we can redefine everything, continuity, convergence, compactness, using only these little bubbles that we're talking about. So we won't say distance is less than epsilon. We'll say something. The preimage of an open bubble is an open bubble, okay? And this allows us to liberate everything, because it allows us to do calculus on shapes that cannot be measured. What only matters is the connection of the shapes, in other words. We have really severed the dependence on the ruler by doing this. So let's get into the technical, I guess, details. This is a little, I'm trying to find the best way to motivate this, but we need to look at something called metric spaces first before we go to topology. We need to generalize the distance between x and y to an abstract distance function. And we'll say a metric space is a pair, x comma d, where x is a set and d is a Cartesian, is just a product of the sets, mapping to 0 and infinity, okay? And it's a function, because distance, right, can be either 0 or infinitely large, right? A function, it's going to be a function satisfying three laws, okay? The metric space. It's going to be identity, so that distance is equal to 0 if and only if x is equal to y. Does that make sense? If you're on the same point, then there's no distance between them because they're the same point, right? So it's 0. Symmetry. So we're going to say that it doesn't matter if we measure x first or y first, you know, the distances between them is going to be equal, right? For a metric space. And then lastly, the distance is in a more abstract form, you know, needs to be defined by some kind of like triangle or whatever, okay? And what that means is the distance between x and z, right? If we have it in terms of x and y, and then y and z, you know, this is a more general way to think about it. Constructions on the metric. So in terms of the metric, we can come up with things called, the metric space, we can come up with things called the open ball, which is just a set of everything in x given, you know, some distance is less than r, okay? And remember, it's strictly less than r. So the open ball is like, you can think about it like a little sphere, I guess, on the set of X, right? And it doesn't include the boundary of like being r some radius far away, right? But the open ball r, it just kind of generalizes this. The open set, so we'll say a set of U is open for everything in U if there exists some epsilon, okay, such that the open ball of or the open ball of epsilon of X is a subset of U. So that basically means every point has a safety bubble inside the set, if that makes sense. So this allows us to, continue from our little adversarial game, but instead do this with sets. All right, we're getting a more general way to do this, or to construct limits and such. Okay. Next is the closed set. This is the complement of an open set, so it just means whatever is not in the open set. Okay, so that's a closed set. Okay. And then the neighborhood of X. So this is just any open set. Remember, any open set containing X. All right, so that would be in the neighborhood of X. All right, it's an open set that contains whatever is in X. All right. The interior then of some set, right? Let's just call it. I mean, it should really be U, but if it's the interior of A would be, again, we can take it as an arbitrary kind of set within that, and it is the largest open set contained in A. All right, and closure would be the smallest closed set containing A. And what we would then say is the boundary, of A would be the closure of the set intersection. So A is a particular set within X, if that makes sense. And what we're doing is we're saying the intersection of the closure of that particular of X there with X within, or X taking out A, and the closure of that. That is what we formally define it as the boundary. Okay, and the boundary in and of itself is a set. Okay, you're not really going to get the full intuition for this until you really read through this yourself and work through some practice problems. But I hope this gives you a little bit of an idea of what we're doing, because this is going to allow us then to show something called work through different metrics. Okay, so there's discrete metric, trivial metric, standard metric, and real metrics, and then something called the Manhattan metric. So how you can think about this in terms of the definitions that we have here is that if the distance is 1, right, if the distance is 1 and x is not equal to y, and the distance of x and x is equal to 0, we can say that the ball, right, of radius 1/2 contains only x, and therefore every little singleton is its own open set, and by union every subset of x is open. Okay, this is we're essentially getting metrics in terms of all of these definitions here. The trivial metric, let's say we have the distance between x and y is equal to 0 for all x and y. The reason this is trivial is because only the empty set and x are open in this metric. So continuity is trivial, right? But separation is impossible. If we look at a metric on the real numbers, okay, instead of just, in terms of the abstract definitions, say the distance is equal to the absolute value of x minus y. This recovers everything that we've had so far. All right, there's nothing interesting that happens. Open intervals on a comma b are open balls. All right, and they're just again, the open balls would just be this. All right, it's the trivial one, or it's not trivial. The trivial metric is here, but the standard metric on the real numbers. But let's look at a specific Euclidean metric instead on the real numbers, but real numbers in dimensions. Okay. Well, then the distance between some x and y would be the x and y for each of the coordinates on, let's say, for n, real numbers, all right, or for the dimension, for the real numbers with a dimension of n, and the distances would be defined in terms of the square root of this, of the sum of all the, x squared, y squared, z squared, whatever. Okay. Open balls then would be familiar disks at n equals 2, or balls where n is equal to 3. So again, the disk would look like, where n is equal to 2, this would look like just a disk, right? And then balls would look kind of like a sphere, etc. But this is Euclidean metric, right? Last thing we'll go over is the taxicab or Manhattan metric. The reason why is because, like, we would define distances in terms of like how much they have to walk, because we can't walk through skyscrapers, if that makes sense. So you'd like walk on the road and then have to walk on the sidewalks or whatever. And this would be on R2, right? We're two-dimensional real numbers, okay? And the open balls themselves become diamonds, all right? Think about it. Really the only way to get from, or the closest way to get from, the point that you're at to the next one would be just, straight diamonds, right? So the topology is the same really as Euclidean, though, and it's all the norms on finite dimensional spaces are really equivalent, even though we chose a different metric. So topologically, they're the same thing. And so even though we have different metrics, we achieve something really similar for Euclidean on N2, okay? Now that we've mentioned topology, let's define topology. So what this means is if we strip away the metric D and keep only the open sets, okay, we only care about the sets themselves instead of the metric. A topological space then would be a pair. Okay, it would be defined as a pair of X as a set, and tau. Tau is a collection of subsets of X, and called open sets. Okay. Remember how we defined open sets up here. U is open if for everything in U there exists some epsilon. Remember, epsilon such that the ball, or such that the open ball is a subset of U. Okay, every point is a safety bubble inside the set. Okay. So now we'll say topological space, getting rid of the metric. We have three things now instead, a little more simple. We have triviality, which is that the empty set, of course, is an element of tau. Okay, and X also will be an element of tau. So this is the key move that we have here. X itself is an element of tau, which gives us the topological, or it gives us the topological, or the space that's defined by the pair. Okay, that's the key move. And we have the unions also of any collection of open sets is open. Okay, and the intersections of finitely many open sets is open as well, okay? And what this allows us to do is create mappings. So let's define continuity in terms of this new way of doing this without limits. We'd say a map F, if we have, X that is a subset of the tau, okay? And we have some topology, and we want to create up a mapping to a new topology. We would say, and it's called Y, we would say it's continuous if the preimage of every open set is open, okay? And what that means is that for all V within the topology, or the topological a primitive tau sub Y, if we take the inverse of everything within Y, and that is an element of the other topological space, that allows us to define continuity. Okay. This definition requires no limits, no epsilon, no delta, and it's purely set theoretic. And that is the whole function of what it means to take away distance and just keep this initial move that we made for open sets, because we're saying there exists an epsilon within the definition of an open set, okay? And we have the containment of the open balls within that open set, okay? That's the very definition of how we're doing it, all right? And of course, we're not really, it's not purely separate from no epsilon, etc., no delta, but it allows for a much more convenient mathematical way to talk about these concepts, right? So let's look at the metric topology. Let's say any metric space will induce a topology, okay, where tau is a collection of all unions of open balls. Under this topology, the epsilon delta definition of continuity matches the topological one exactly. And I would like you to go, that's basically your homework, to go look at that and see why that works. Now, there's something called the Zariski topology. And this is the foundation of all of something called algebraic geometry. Basically, it means that if we have the set X and it's equal to the real numbers, we can define open sets to be the empty set and any set U such that the real numbers quotiented by any set U is finite. Okay? And this is a really strange thing, and it's very counterintuitive, but two non-empty open sets must intersect. So it is impossible to separate 2 points with disjoint open sets, and this is what we call a non-Hausdorff space. All right? Another cool example is something called cofinite topology. So on an open set X, open sets are those with finite complement. Okay, so that means that the complement of the set is finite, of course, plus the null set or the empty set. Okay, this has an interesting property that is compact, right? Because the complement's compact, right? Or the complement's finite. So any cover by opens with finite complements has one, and by the way, a cover of set is just something that completes the set after union, after all the unions, okay? This is a general, we'll talk about bases in a second. Oh yeah, there's bases. We'll talk about this in a second. But any cover by opens with the finite complements has one containing all but finitely many points, add infinitely many more. Okay, this is very, very powerful. Cofinite topology. I meant finitely many more. Sorry, not infinitely many more. Okay. So yeah, it would be for a cofinite topology, it would be compact, because you can only add finitely many more. All right. Let's talk about a basis for topology. So a collection B is considered a basis if the union of the basis gives you the set X. Okay, and so what this looks like is for B1 and B2 that are in the collection. Okay, and for all of the things that are in the intersection of the collection, there exists another basis in B with the stuff that's in B3, okay, as a subset of the intersection between B1 and B2, all right? And what this allows us to do is describe open sets as unions of basis elements, okay? And what we can now say is that open balls allow us to describe allow us to form a basis for any metric topology. And in general topological spaces, limits are not necessarily unique. So to fix this idea, right, because obviously we wanted to find one particular unique limit, we impose something called the Hausdorff axiom, all right? And this axiom says for any distinct x and y within our x, there exists disjoint open sets such that the things in U and the things that are in Y, or sorry, the things that are in V are disjoint from each other, but they also can be members of the metric topology. Okay, so the theorem that follows from this is that in a Hausdorff space, limits of sequences when they exist are unique, and metric spaces are always Hausdorff. All right, and that's the theorem that follows from just having this one axiom. So trivial topology, though, the trivial topology is not Hausdorff. All right, and that's something to keep in mind as well. Now let's talk about compactness. And what compactness really does, we used it a little bit earlier, but it allows us to generalize closed and bounded. And it captures the idea that a space is finite-ish, okay? So what that precisely means is a set K is compact if every open cover of K admits a finite subcover. So if you try to cover K, or if you try to express the entire set K with finitely many patches, you can always throw away but a finite number of them and still cover K. All right? So this is how we're defining compactness. If we throw away a finite number and still cover K, you can do this with infinitely many patches. So let's look at this. The Hein-Borel theorem, and this gives us the link to the real numbers in dimensions. A subset of Rn is compact if and only if it is closed and bounded. All right. So let's say we have a finite interval a to b that is a subset of the real numbers. We can first assume that we have a finite, the finite interval has an open cover, okay, with no finite subcover, all right? And this is how we're going to try to prove this. So everything that's contained within this, if we union over alpha, we will get the full cover of the space or of the set, and we'll bisect into some A and M and B. Okay, so we're bisecting the interval with it, and at least one half must have no finite subcover. If we repeat this infinitely to generate the nested sequence of intervals I sub n with lengths shrinking to 0, by the completeness of the real numbers, these intersect at a single point C. And since the set of U alpha covers this entire interval, okay, some set U of beta contains C. And since U of beta is open, it contains the entirety of the interval I sub m for a large enough n. So we get a contradiction because we assumed that the interval I sub n had no finite subcover, but we just covered it with a single set U sub beta. All right. So in general, the real numbers in dimensions are embed in a large cube. We can use repeated bisections in each coordinate. It kind of it reminds you of Zeno's paradox, right? It reminds you of the, I guess, mechanics in which Zeno, constructed his paradox. But instead, we're using it as a proof sketch to show that a subset of Rn is compact if and only if it's closed and bounded with the metric topology, just as a consequence of the metric topology. Okay, so let's look at a non-compact interval. We would say 0, comma 1 is not compact if we cover it by 1 over n, comma 2 for n is greater than or equal to 2. It has no finite subcover. All right. And we can also arrive at something called the continuous image theorem, which just shows us that the continuous image of a compact set is compact, and so it'll inherit that property. And you can look at this, right? If we make a mapping from this set to Y, and if the set in a compact set is a subset of X is it's compact, right? We used K as a compact set. If we let V sub alpha be an open cover of the function of the compact set, since F is continuous, each preimage is open in X, and we form a open cover in K. All right, and since K is compact, we can extract a finite subcover V sub 1 all the way to cover the entire set, and so then V sub 1 to V sub n is a finite cover of f of K. All right, this then, using the topological properties, we then generalize the extreme value theorem. All right. The continuous ruled function on a compact space attains a maximum and a minimum. So essentially, we can prove this in terms of the image f sub k is compact in R, is hence closed and bounded, and attains a supremum and an infimum. Okay, so that's great, and in fact, we can get that the sequential compactness in the metric spaces gives us that the compact set is sequentially compact if each sequence in K has a convergent subsequence. All right, this is another important property that we can use to then say equivalence or describe equivalence, because if for metric spaces, if it's compact, if and only if it is sequentially compact, if and only if it is completely ordered. All right. Completely and totally bounded, if that makes sense. Okay. So totally bounded plus complete implies sequentially compact, and then totally bounded implies for any epsilon 1 over n cover by finitely many balls of radius 1 over n, and you can construct a diagonal subsequence converging by the Cantor diagonal argument. Okay, this is a fun thing to try to work through. I think you can find the proof for this in a textbook, but definitely commit some time to working through this proof. But that's the general outline of how this works from a logical, standpoint. Now let's talk about connectedness. We will say that X is connected if it cannot be written as the union of two disjoint non-empty open sets. Okay, so again, we're going to use the Hausdorff axioms. An equivalent way of stating this is the only subsets of X that are both open and closed, and they're called kind of like clopen, right, are the null set and X. All right, the empty set. All right, I keep saying null set, but empty set's a lot more standard. So for example, the real numbers are connected. The reason why is because if we suppose the real numbers are disjoint, open, and non-empty, okay, and that's what this symbol means. Okay, it's kind of shorthand, so you get the little square union thing. They're disjoint, open, and non-empty. Pick something within A, something within U and something within V, with A is less than B. All right, and then if we suppose C is the supremum of everything in the interval, the intersection with U, since U is closed on the finite interval, being the complement of V, right? C is in U, and since U is open, C has a neighborhood of C minus epsilon, comma C plus epsilon is a subset of U. this implies C is not the supremum. We can actually go higher and stay in U, or C touches V. And this gives us a contradiction because that implies the split is impossible. All right, so that's how we know that the real numbers are connected. Okay. So we can look at something called the topologist sine curve. And what this looks like is if we take the set, right, of the ordered pair of x comma sine of 1 over x, okay, given some like positive x, and the union of that with the ordered pair 0, 0, okay. So we've taken the set of this union, the set of the ordered pair, path connectedness component of u comma u is a singleton, but the set is connected, so we cannot separate the vertical line from the oscillating part. All right, let's look at Tychonoff's theorem, which tells us this is called the finite case 2 lemma. This is another interesting kind of topological construction, but the product of finitely many compact spaces is also compact. All right, so if we take two spaces x and y, and we take their product, right, and they're both compact, the cover of x and the product of x and y by open tubes, okay, we're calling them open tubes, which just become like little product spaces where u is open in x, okay, so we're taking open sets in x and then taking the product space of that. All right, for fixed y, let's say u given some x and y are a subset of this new or even there's some like just they're within the graph or within the product space, right, or product set. If for a fixed y it covers x, then it has finite subcovers 1 u comma 1 all the way to u comma n, or u sub n. The tube, which would be the union of all the finite subcovers with the product of v of y, or v of y is the neighborhood of y, it covers a strip. This covers compact y by finitely many v sub y. Okay, so that's a pretty interesting proof sketch. I think there's other ways to prove it as well, but this is really the most logical way to do this. So we have now really successfully severed the dependence on distance to describe metric spaces, right? Because compactness, in a general sense, right? Because we really don't care about closedness and boundedness, but really every open cover has a finite subcover, all right? And continuity is no longer delta epsilon, but pre-images of opens are open, all right? And of course, the open sets are defined in terms of balls and everything, all right? But keep in mind, this allows us to not have to really rely on the, or play the game every single time we want to define a single limit, right? This allows us to generalize when we take special cases, all right? So really, we're now ready for spaces without global coordinates, all right? Curved manifolds, function spaces, quantum field configurations where no global metric exists. So this is really the mathematical tools that, you know, you should really invest your time in understanding, because it builds your mathematical maturity to start handling things without coordinates, okay? Now that we understand space, okay, in a really general sense, let's look at the change in space, all right? So remember, at the very beginning, we had single variable calculus, right? The derivative is a number, right? It's the slope. But the real world is multidimensional. So what is the slope of a mountain range? All right. Well, that becomes kind of the question that, you know, we want to describe, right, because the physical world is not, just some abstract topology. We want to describe change, and this notion of slope is going to be replaced by a linear map, right? This is the great insight of multivariable calculus. The derivative is not a number, right? It is a matrix. And when we differentiate a function in Rn, we're finding the best linear approximation of that function. We're replacing a difficult, curved, nonlinear world with a simple kind of flat world where we just care about the algebra of lines, right? In other words, a differentiable function near point A behaves to first order exactly like some linear map. And this linear approximation, we call it the total derivative, all right? And what's cool about that is if that linear map, which is actually the Jacobian matrix, okay, is invertible, if we can invert that linear map, then the inverse function theorem, we call it the inverse function theorem, tells us the original curve function is invertible too. And this is the bridge between, linear algebra and calculus, okay? But we actually don't need linear algebra at all, because if linear approximation works, the reality works, but we can actually generalize further to just topology, all right? So that's kind of the caveat, right? Usually we're taught linear algebra, here's your Jacobian matrix, everything you need to know, like, yeah, it's lines, great. But we're missing that further analysis, right, of the continuum itself. So remember, differentiability in single variable calculus, it means that if we have f of a plus h, f of a plus f prime of a times h plus r of h, where this remainder vanishes faster than h, all right, and we can show this. But in multivariable calculus, h, this arbitrary parameter becomes a variable, and we cannot divide by a vector, okay? So we demand then that the norm of the remainder here, the norm of the remainder here, will vanish faster than the norm of the perturbation. And the perturbation just means, how we're varying it from the initial, linear amount, okay? So the derivative, f prime of a, is no longer a number, again, but it's a linear transformation acting on the vector of our infinitesimal. Let's be rigorous now. Say, let U, given that we have some topology background before going into this, U is a subset of the real numbers in n dimensions, all right? And it's open. Let U map to R of M, and A just be something that's in U. Well, this allows us to define Fréchet differentiability. F is differentiable at A if there exists a bounded linear map, of course, with this D acting on f of A, such that the norm of, again, this has come back with the norm of this linear form divided by the norm of H itself is equal to 0. And this denotes any norm at all, equivalent in all infinite dimensions. So d of f of a is the total derivative or differential at a. And in finite dimensions, norms are equivalent, so this definition is coordinate independent. Okay? That just means it doesn't matter what we choose as our coordinates, this definition always holds. Okay, it's general. So let's say we choose some bases or some bases for Rn and Rm. The linear map is represented by the m by n matrix of partial derivatives, okay? So J of f of a would just be an m by n matrix that, just in terms of the coordinates that we chose for the map that we're trying to make. If all partial derivatives exist, okay, and are continuous, then f is said to be Fréchet differentiable and belongs to this set of continuous functions that are first differentiable, okay? And partial derivatives always give entries of the Jacobian when they exist, but existence of d of f is stronger than mere existence of partials, okay? So this gives really strong existence because we have a topological definition of differentiability. So let's look at some linearization. So for this function here, let's say f of x and y would give us, you know, a scalar function that, you know, outputs, you know, R2 to R2. Okay, so let's assume that it gives us a two-dimensional output. You know, we give it two-dimensional input, it gives us two-dimensional output. Let's compute d of x, the derivative of this scalar function of multiple variables. So what we first do is perturb the input by a vector h, which is h1, h2, okay? And we'll expand the terms out. And what that looks like is we directly put that into the function. There's the comma there, so you know we expanded this out. What we want to do is isolate the constant part and the linear part and the remainder, and to get it into the form that we want. So the constant part, remember, is just the original function. It's linear in h, so we took these linear parts, and then the remainder actually becomes quadratic in h for these. And all we have to do is just verify that this remainder, or the norm of the remainder, is less than or equal to whatever we get factored out here, which is less than or equal to 2 h squared. And the norm divided by h approaches 0. So what we have is that we can construct the matrix itself via the Fréchet differentiability, the strong definition of differentiability in multiple dimensions. Okay. So yeah, and then we get the derivative itself just became a matrix. All right. Now, what we have here next for polar coordinates, assume that we have a function that describes a radius as a function of some angular coordinate and some rho radius, okay? And this radius is greater than 0. The Jacobian then will look like cosine, cosine, negative sine, sine and negative sine, but with the rho over here. And that Jacobian acting on the radial function will have a determinant of minus rho. And since rho is greater than 0, the determinant is non-zero, the map is locally invertible anywhere away from the origin. This makes sense because we are restricting ourselves to the polar coordinate case. Let's look at how the chain rule applies, which we didn't really discuss this earlier, but I'm assuming some basic calculus foundation, okay? If you made it this far, all right. Differentiability or differentiation converts function composition into matrix multiplication, all right? So we would say, you know, g is differentiable at a and f is differentiable at g of a, then we would have that the composition of the functions here would result in just the Jacobian matrix of f of g of a, and then, you know, it looks analogous to the regular chain rule, but just it becomes a linear approximation for both f and g, all right, with the particular matrices. And the linear map would then just become L of M, and they're acting on each other, okay? The full proof, you know, will look like this. And of course, we would want to bound this. You can walk through this yourself. I'm not going to walk through the whole thing, but take my word for it, all right? Now, the theorem 2, we again can get our mean value inequality. Okay, so there's no exact mean value theorem anymore for vector functions. Equality doesn't really fail. I mean, it doesn't really work, but we can actually construct a bound. Why? Because we're defining everything in terms of limits, right? So for f, this differentiable, well, not really limits, but in terms of open sets. So if it's differentiable on compact interval, we would say that the norm of the difference between the function in two different places on this interval is less than or equal to the supremum on this for some, you know, for some element that's within the interval x, okay, where all we have to do is take the product of the derivative of that function, okay, and the product of the derivative of the function and the difference between the interval, but the norm of both, okay? So we take the product of the norms of the difference between the interval and the derivative, all right? And if you want to prove this, you can consider some function gt that allows us to, parameterize the interval here, where, t belongs to some between 0 and 1, and this is very useful because we can then say, well, at 0, this is kind of like a convexity type thing where, where this is 0, that becomes just a, but if it becomes 1, we can subtract off the a and get left with f of b, okay? So it maps perfectly in the way that we want it to, and you can prove it this way. This is the core. This is probably the most important thing that you will see in this video, which is one of them. This video is going to be massive, but the inverse function theorem, which is the core of analysis, is really the bridge of linear algebra and calculus, because and really what this allows us to do is say, if we have a set, right, that maps the real numbers in, and if it belongs to the first differentiable continuous functions, okay, the function describes this map. If the linear map of the derivative acting on f of a is invertible, then f is locally invertible near a. So that means is there exist neighborhoods, okay, such that when we map v to w, there's a bijection with a first differentiable continuous inverse, and the derivative acting on the preimage of the image of the function is equal to the inverse of the derivative acting on the function there. You see what I'm saying? So we can essentially show that the basically we can contract, we can do like a contraction mapping. So if we want to prove this, what we first want to do is translate the coordinates. So let's say a is equal to 0, right? So that f of a is 0. And then d acting on f of a would map it to some capital A, all right? And let's say we want to solve f of x is equal to y, all right? We can rewrite the equation as a fixed point problem. So define a map g of x, okay, that's equal to a minus the invertible or the inverse of a, okay, or acting on f of x minus y, okay? And if g of x is equal to x, then x minus a inverse of f of x plus, distributing this through the parentheses, f a inverse acting on y is equal to x. That implies a inverse acting on f of x is equal to a inverse acting on y, which implies that f of x is equal to y. And then we can compute the contraction, okay, which is when we decide to do the derivative operator on this map that we've constructed here, okay, which will first give us the identity. And then it would, because again, right, if you do a derivative acting on x, you'll get, the identity matrix subtracted off a inverse acting on the derivative acting on f of x, which then would give you a inverse acting on a minus d of f of x, okay? And as you can see, of course, you can factor this out because it's equivalent because of the identity matrix. And since since f is continuous and differentiable once, and d of f of 0 is a, okay, for small x, then the norm of d of f of x minus a is small. And if we choose some r small enough, okay, that for this really acts like kind of like delta, but the norm of h, which is less than 2r, we can then create this inequality in terms of what we had previously. Then the derivative operator acting on this map that we defined, or the norm of this, is small and is less than 1/2. So by the contraction mapping principle, the g has a unique fixed point, and thus f of x is equal to y has a unique solution. All right, and we can further show how this gives us then g of h minus g of k is less than or equal to 1/2 of h minus k by going through. But essentially what this means logically is contraction implies that there's a unique fixed point, which implies local invertibility, and differentiability of the inverse follows from chain rule and implicit theorem. Okay, so that's kind of a lot, but again, let's go back to the statement and why this makes intuitive sense. For the function, right, u mapping to r, and if this function is first differentiable and continuous, if this map is invertible, then it's locally invertible near the point. All right, okay, and that there exists neighborhoods, again, with a and v and f of a and w, such that if we define this map, again, that's the g, right, is a bijection, again, and we can construct this equality. All right, now that we have constructed the contraction mapping, or in terms of the inverse function theorem, and now that we also have basically the chain rule as well as mean value inequalities, etc., where is this leading? Well, let us describe then what's important. What's really important is that the matrices here are invertible. This allows us to do a lot of fun things with our mappings and allow us to do calculus with linear approximations and such. So let's describe GL in comma R to be the set of invertible matrices. Let's consider the determinant map, right? And what the determinant map looks like is if we have m sub n mapping to the real numbers, okay? The derivative of the determinant at identity is its trace, okay? So that means that the derivative acting on the determinant at identity is going to be the trace of that determinant, okay? Or is going to be the trace of that matrix. And since trace is something we call surjective, right, onto R, which means everything from here is going onto the real number, the real numbers, the inverse function theorem implies then that the determinant, right, or that the inverse determinant, right, because of the inverse map, the inverse mapping, is the real numbers excluding the 0, the set of 0, which is an open set. So what that means, consequently, that means that the set of invertible matrices is something we would call an open manifold. All right. What we can then have as a consequence of something we call the general linear group okay, and determinate map, is that complex exponentials we can define as the complex map of z onto ez, okay? Consider a scalar function where we have e of x cosine y and e of x sine y. The Jacobian looks like this, and the determinant is not equal to 0 everywhere, and hence, because there's no 0 determinant anywhere, we have this is globally invertible on the complex numbers, okay? And we didn't really construct the complex numbers, but and we'll discuss this a little bit more towards the later in the video, complex analysis. But this plays a really important role because complex numbers are inherently a constriction or restriction on R2. Okay, but we really get an entire exponential from this, and a very clean looking Jacobian, as you can see. Look at the massive symmetry. Okay. Now let's look at the implicit function theorem. All right. So say if we want to solve equations where we have some capital F of x and y is equal to 0 for little y, let capital F be the product of these two real spaces, and let that product map to just RK, okay, with R with dimension k, and it's continuous and differentiable. The ordered pair A and B with f of A and B is equal to 0, and the derivative acting on f A and B is invertible. There exist neighborhoods, okay, with A being U and B being V, and a unique continuous function G, where if we map U onto V with the function in terms of we're parameterizing this G function in terms of x to be equal to 0, and G of A is B, okay? We can then really construct this implicit function here, all right? So consider the map first. If we take the derivative of the map, let's say we have this ordered pair with the identity and then 0, and then the derivative of x with respect to x, and then derivative with respect to y on f, the block-lower triangular determinant becomes not equal to 0, okay? And it is locally invertible near the A and B ordered pair. So the inverse will then have a form of x and then comma eta x and y, which is a function of x and y. And if we set y to be equal to eta of x comma 0, that gives us g of x, okay? So this is how we can prove that there exist neighborhoods and a unique function g that allows us to do this, okay? Let's look at the circle. So here's f of x and y, and it's just, x squared plus y squared, minus 1 equals 0, all right? If we take the partial derivative just with respect to y, okay, the total derivative, or sorry, the partial derivative with respect to y, we get 2y. And at 0, comma 1, 2y is equal to, 2 is not equal to 0, so we can solve for y, and in terms of x, and we get the square root of 1 minus x squared. At 1 comma 0, 2y equals 0, and invertibility fails, and the vertical tangent means that y is not a function of x there, okay? So that's how we can use this for the circle. There's another theorem called constant rank theorem, and we would say that d acting on f has constant rank near y. Then there exists local coordinates u comma v near a, and s comma t near f of a, such that f of u comma v is equal to u comma 0 in the new coordinates. In other words, we can basically do like a fancy multivariable u sub, okay, or substitution of variables by using the inverse theorem on projections iteratively, okay? Next thing is we can use the regular value theorem, which says that if we have a function that, we're mapping onto n dimensions to k dimensions where n is greater than or equal to k, okay? In general, c is a regular value, meaning that if we differentiate the function, it's surjective for all x that's in the preimage, okay? And the level set should just be where essentially all the derivatives, this particular kind of like, if you can think of like mountains, and like essentially where all the derivatives would be kind of like equal to 0, their level sets, or just like the places where they have equipotential lines, or like, the same kind of height, in other words. The derivative of p would be surjective, which implies that the kernel dimension would be n minus k. And by the rank theorem, locally f looks like a projection of r to the nk cross rk. That is a mapping into the k dimensions, and the level set becomes r to the n minus k with a product of the set of zeros, okay? The last thing to understand is the sphere. And what the sphere allows us to do is, if we have a function which is just, the norm of x squared, the level set is just f inverse of 1, and that's the sphere of s of n, okay? So if we differentiate f of x of h, we'll get 2h, or 2x times h, and this is surjective, which means it's non-zero for all x is not equal to 0. Since no point on the sphere is 0, the sphere is what we call a smooth manifold. All right? Hopefully, I might have lost you probably towards the end of this section, but you now understand that, the power of defining differentiation as linear approximation. Okay, and the validity of the linear map invertibility guarantees that the validity of the nonlinear map local invertibility, okay, is given, okay? And that's the heart of what is known to be differential geometry. And it comes from analysis, again, of the continuum. And this allows us to construct coordinate charts, and they exist because the derivative in and of itself is invertible. We get higher order behavior that's captured by higher derivatives, but the first derivative already carries immense power just from first continuous functions that are first differentiable. Okay, so now we're going to try to describe complex analysis and analyticity, or analytic functions, as a special case of R2, okay? Or, yeah. Now, we're going to commit to kind of a strange turn, because we have multivariable differentiation on the real numbers, okay? And then Fréchet derivative provides the best linear approximation, and we can the invertibility yields local coordinate systems, which are really nice, right? So, but really, a function can be infinitely differentiable yet nowhere analytic, oscillate wildly, or use global extension. So you can modify a smooth real function locally without affecting it far away using something called bump functions, all right? So that's, that's kind of like a little problematic. So what we want to do is propose something called the complex plane, right? And it seems like really we're only adding one minor requirement to the complex plane, which is that the derivative exists and is independent of the direction of approach. Okay? And that requirement forces the function to obey all of these things here. Okay? So if it's differentiable once in the complex sense, it is infinitely differentiable, it is analytic, so that means it's equal to its Taylor series everywhere. It is harmonic, that means it satisfies the Laplace equation. It is conformal, that means it preserves angles, so where the derivative is not equal to 0. And it is rigid, that means that it's determined in the whole domain by its values on a tiny arc. Now, this kingdom, really, that we're constructing of rigidity, we showed that a single complex derivative is stronger than any finite number of real derivatives. And, you might just think of complex analysis as just calculus with I, right, with the negative square root of -1. But for the real world, you can have a function that is smooth, really, again, in one spot and jagged in another. And real functions are just too flexible. So if we demand that the function is differentiable in a complex sense, we impose this constraint. And the derivative must be the same wherever you approach it. This obeys the Cauchy-Riemann equations here, all right? And this allows us to, again, multiplication by a complex number is a rotation and dilation. As a matrix acting on vectors, it looks like this. And the matrix has only 2 degrees of freedom and a specific subset of all linear maps that are possible. So you basically, the complex number imposes an overdetermined system of partial differential equations on the real and imaginary parts. Okay? And that's what that looks like. Okay? That's the Cauchy-Riemann equations. If a complex function then is differentiable once, it is differentiable infinitely many times. It is analytic. And again, analyticity means that it's equal to its Taylor series everywhere. And it becomes rigid. So if you know the values of a holomorphic function on a tiny little arc, you know its values everywhere in the universe. And it's essentially like a hologram. This is why complex analysis is essential to physics, in other words. It describes fields that are structurally perfect, okay? So, again, let's define holomorphy. So the definition will be, let's let omega be a subset of the complex plane, and that's an open set. So if we map omega to the complex plane, it is holomorphic or analytic if it is complex differentiable at every point z0 in omega. Okay? And of course, we're just using the limit definition of the derivative. But if it exists in the complex plane, the limit must exist and be the same whether h approaches 0 along the real axis or imaginary axis or any spiral. All right? So let's look at f of x is equal to z squared. If we substitute this into the limit definition, okay, by doing this numerator first, okay, we can then have that the limit is to z0. So that means that, it's holomorphic everywhere because it matches. F prime of z is 2z. But let's look at the real part only of z. Okay? And if we take some path in the real axis and say, let's let h be real, we have 1. But if we take h to be negative ik, where k is real, and just change our path of approach, we get 0. The result is 1 is not equal to 0, and the limit does not exist. That means that the function is nowhere holomorphic. Okay? And all we have to do is just show this. We don't even have to show the Cauchy-Riemann equations, but of course it's not going to work either. If we look at the conjugate, though, let's say we have the magnitude, let's say the conjugate of z, which would be z minus iy. It also, doesn't work for the conjugate. Okay, so it's nowhere holomorphic despite being continuous everywhere. All right. So we're really, really restricting the domain or the functions of interest. Let's look at the first theorem for the Cauchy-Riemann equations. F is holomorphic if and only if u and v are real differentiable and satisfy this. All right. So, and satisfy the set of partial differential equations. Okay. Now, what that means is if we let the derivative of the complex variable, a function of a complex variable, to be equal to some limit, which is just a complex value. If we were to approach it along along the real axis and the imaginary axis, and we equate them together, this implies the harder direction, which comes from the Luhmann-Minchoff theorem or Menkoff theorem, and we can accept this condition here. But that's essentially how you would prove the Cauchy-Riemann equations. If we look at the exponential map, so let's say e to the z, this would be equal to e to the x multiplied by cosine y plus I sine y, and we can show this satisfies the Cauchy-Riemann equations and it's holomorphic everywhere. Okay, and this went back to our original finding with the linear map. Okay, and so that also kind of relates to what we're looking at. Now let's look at Kersadt's Cauchy theorem. We'll say f is holomorphic in a simply connected domain, omega, and gamma is a simple closed positively oriented contour in omega. Okay, remember omega is an open set. So if it's simply closed positively oriented contour, the integral of that function on the contour is equal to 0. That means that a holomorphic function is what? It's a conservative vector field. Okay, and that just means it's irrotational and incompressible. Okay, so we get a nice physical intuition for this. So let's look at this for a triangle, and if we parameterize the edges, let's say we have a function of a complex variable, and we integrate it with respect to some d zeta, and assume that it exists, locally by holomorphy and chain rule. We, the full version would be done by deformation and subdivision, but essentially you're going to integrate the function around the boundaries, and you get the integrand for the function at the vertices should be equal to 0. Okay, and that's what you should find. If we try to integrate the conjugate of z, okay, and we parameterize z in terms of complex values here, so we'll have z, and then dz is e to the I d theta, and the complex conjugate of this is e to the minus I. We can confirm again that z is not holomorphic by using this because the integral around everything is 2 pi I and it's not equal to 0. Okay, so again, this is another way to check if function is holomorphic because it's also a conservative vector field. Okay, now let's look at the Cauchy integral formula. Values inside are determined by values on the boundary, which means that if f is holomorphic inside and on gamma and z is inside, we can differentiate under the integral sign infinitely many times. And the consequence of that is that if f is differentiable once, it is differentiable forever. Okay, and so that's the closed form formula for doing this. So we can try to prove this by saying, let's consider a function, that is f of zeta divided by, zeta minus z, or zeta is not equal to z, then this function of z would be equal to the derivative of f of the derivative of f of z. G, if we consider this setup, G holomorphic inside of gamma, assuming it's a removable singularity, if we take the loop, or if we take the integral around the loop of G, that should be equal to 0, right? And so all we have to do is subtract the contribution to the singularity, which is the 2 pi I f of z. Okay? And so that's very nice. Every time, we, wrap around singularity, all we have to do is just subtract the contribution, because it's just the nature of G. Okay? Now, if we compute this integral here, okay, of course, we can look at this and be like, oh, there's a singularity, right, at z equals 1, right, because 1 minus 1 is 0, right? But if you factor the numerator instead, you can get the integrand to simplify to this with a removable singularity, and it's a polynomial, and it would be holomorphic everywhere, and just you can use Cauchy's theorem, okay, and the integral is 0. So there's some ideas that you can look at instead of having to use the singularity formulas and everything. Okay. Also, let's look at Liouville's theorem. Liouville's theorem follows from complex analysis as well, because if we bounded entire functions must be constant. So what that means is that if a function is bounded, let's say that the norm of f is less than or equal to some m, right? Use the integral formula for the derivative on a giant circle of radius r. And what that means is the Cauchy estimates on a large circle, which is the norm of z, is equal to r. Well, we can then have that the norm of the derivative of the function at z naught is less than or equal to factorial times that bound, right, divided by r to the n for any n. And so if we let r go to infinity, then it becomes 0, the derivative becomes 0 everywhere, and it's a constant, okay? And this actually gives us a one-line proof for something called the fundamental theorem of algebra, which the fundamental theorem of algebra basically tells us that we can factor any polynomial, or that all polynomials have, the same degree of solutions that they do for like every single polynomial of degree n has n many solutions and stuff. So that it's deep. Liouville's theorem is deeply connected to algebra and number theory and all this stuff. And you're going to see this later on we're going to call back on this theorem for more episodes. The next episode we're going to talk about is algebra and invariance. Okay, and we'll talk about these things. But just looking ahead, entire functions. So we'd say sine of z and e to the z are entire and unbounded. Polynomials are entire, non-constant, unbounded. Okay, so there's just other classes of functions. And there's another generalization called the maximum modulus principle. So if we have a non-constant holomorphic function, it cannot have a local maximum of magnitude of f of z inside its domain. It acts like a harmonic sheet. So if you push one point up, it pulls all the neighbors up, and the maxima are pushed to the boundary, right? And you can show this by this logical sequence, which basically shows that we get, the maxima circle implies there's an inequality, which implies there's a constant on a disk, which implies everywhere, right? Because it's holomorphic, okay? Or for a non-constant holomorphic function. We also have the unit disk. You can look at this example as well. F of z is equal to z on a unit disk where the magnitude of the function is 1 on the boundary and is less than 0 inside. Okay. We also have something called the open mapping principle. So for a non-constant holomorphic f is open, images of opens are also open. Okay. And you would prove this with local invertibility, where the derivative is not equal to 0, and you can use the inverse function theorem in the complex plane plus isolated zeros. Okay, so we can use the topology that we grinded out directly in complex analysis. All right, so that's why it's really important, I think, to learn, have some idea of topology before you go into complex analysis. Next is the idea of simply connected proper subdomain of the complex plane, no matter how weirdly shaped or whatever it is. There's a concept of being biholomorphic, so that just means that it's conformally equivalent to a perfect unit disk. Okay, and we'll call this perfect unit disk D. Okay, and what this allows us to do is we can smooth out any simply connected shape into a circle, which is great because it gives us that topological consistency, but also the unit disk is defined in such a way. Okay. Now, you would prove this by just constructing a sequence of normalizations using Montel and Hurwitz to extract a limit map. So an interesting isomorphism that can be made is the upper half plane with the unit disk. And that basically means that we can map the complex variable to z minus I divided by z plus I. And that gives us essentially this isomorphism that's very interesting. And if we look at the theorem 8 for the Schwarz lemma, we can say that if we map the unit disk to another unit disk, it's essentially holomorphic. And if you take the function at a point 0, right, to be equal to 0, then essentially what we're going to have is that the modulus of the function is less than or equal to the modulus of the complex variable associated with it. And if we take the modulus of the derivative at 0, this should be less than or equal to 1. And we get this equality if and only if the function is equal to the complex variable multiplied by some phase factor. Okay, and this is interesting because it shows that if we define some function g again with a removable point, or with a removable at 0 to avoid that singularity, then the derivative of 0 is equal to the function's value at 0. And if you take the modulus of the function, it's less than or equal to 1 over the modulus of z times the modulus of z is equal to 1. On the unit disk, again, taking out the 0, the set of the number 0. And we can extend this by continuity. So then this implies, that the modulus of z is less than or equal to 1 as a maximum modulus. Hence, the maximum modulus of the function is less than or equal to z. And the maximum modulus of the derivative of the function at 0 is less than or equal to 1. So really, what we've accomplished here is pretty remarkable with complex analysis, because we have really have an extremely rigid formalization of local complex differentiability and how it implies global analyticity everywhere. And it's not just, R2, but it's really a new kind of rigid kingdom where functions are allowed to, or they really just obey iron laws just because of a single complex derivative, right? And it's stronger than any finite number of real derivatives. And this rigidity, governs these structures like Riemann surfaces and allow us to describe some new modern dualities in physics, such as anti-de Sitter space slash CF conformal field theory correspondence. Okay, that was recently discovered in like the 60s. Well, not really recently, but more recently-ish. So, okay, this is all good. We have complex derivatives that allow us to, extract nice behaviors out of functions. But we need to find a way to integrate now. And integrate, again, to integrate something is to find a quadrature or area or something, in terms of the continuous functions. But there's a problem because, of course, we have the holomorphic functions, and complex, differentiability implies global analyticity, but the standard tool for integration, which we call the Riemann integral, it's really fragile because it was built on the intuition of just partitioning domain and squeezing a function between step functions, right? So this works great for some continuous function, but it collapses under some things. So take, for example, the Dirichlet function. It's really simple. It's 1 on the rationals and 0 on the irrationals. Okay. It's bounded, yet the Riemann integral fails to exist because you can't define an area under a curve because you're relying on step functions constructed by your domains, right? So it's also incomplete because the space of Riemann integral functions on 0 to 1 is not complete under the L2 norm, which we'll define a little more specifically, but a sequence of integrable functions can converge to a limit that is not a Riemann integrable. And physics, we require Hilbert space of square integrable wave functions. So without that, limits of wave packets can just not exist, right? So Riemann integral needs to die, and the fundamental theorem fails for functions with derivatives that exist everywhere yet are unbounded, right? So what we need to do really is, instead of defining, instead of chopping the x-axis into little widths to come up with rectangles, what we need to do is turn the problem sideways, in other words, literally. So what we do is, instead of partitioning the domain, Lebesgue decided to partition the range. Okay, so by partitioning the range, instead of asking, how high is the function here, you ask how much of the domain is at this height, right? And this is this is a much better way to measure area or measure quadrature, because what happens is you could measure the sides of sets, and since the rational numbers are countable, we can annihilate some of the pathologies. Okay, so Riemann sums, vertical rectangles, Lebesgue sums, we get horizontal slicing. And essentially what this allows us to do is squeeze the graph vertically between upper and lower step functions. All right. So we need to define sets. Okay, so let's say X is a set, and it could be like, Rn, right? And we also need to define something called a sigma algebra. Okay. All the sigma algebra is just a collection of subsets of X that define measurable events. So it contains the empty set. It is closed under complements. Okay, so if we have complements of all the subsets that define measurable sets, it's closed. And It's also closed under countable unions. So if we take all of the subsets and the union of it, it's closed, okay? We're also going to define something called the measure, where the measure is a sigma algebra that maps the collection of subsets to 0 to infinity, and it assigns a size to all the possible measurable events. Okay, so for example, if we have mu of the empty set, that's 0, right? It has a 0 size. But if we have countable additivity, so let's say we want the set of all the possible measurable events, and if they're disjoint, then we can take the measure of the union of all those possible events, and that should be equivalent to the sum of the measure of all the possible events. So we're turning this union of the measure, right, to be equal to the sum of all the measures added up together for those particular events. Okay? And then this allows us to define the Lebesgue measure. And this is the standard measure on Rn, and it extends the notion of volume. So for example, if we want the Lebesgue measure from A to B, the interval A to B, we'd have B minus A. Okay? And it's a complete, translation invariant measure on something we call the Borel sigma algebra. And what a Borel sigma algebra is just it assumes that everything that the Lebesgue adds up to 1 for the interval from 0 to 1 to n. Okay. Now, for measurable functions, let's say we have x maps to R, and that is measurable if the preimage of every interval is a measurable set. So we have a topological definition essentially for x given some f of x is greater than c as a subset of the sigma algebra for all c. Next, we have the Lebesgue integral, which we're defining as a non-measurable function, or for a non-measurable function, the integral of the non-measurable function with respect to the measure is defined as the supremum of the set of the sum of some coefficients that are weighting your measure here, and that you're summing over all the possible outcomes. Given, okay, something we define as a simple function, and we approximate f of x, or we approximate the function in terms of simple functions, and what that means is we take some coefficient times a characteristic function of the set of measurable events, okay? So from that, and we say that it is less than or equal to the function itself. And that is what a simple function is. It's always in terms of characteristic functions, all right? And we only take finite values on measurable sets, all right? So in general, for f, if we split into positive and negative parts, so if we integrate, f and only the positive parts and subtract out the negative parts, it's finite if both the parts are finite, all right, in general. And then let's finally talk about LP spaces. And these are complete spaces where functions now can converge. So this is really crucial for quantum mechanics, right? Because without Lebesgue integration, Hilbert spaces of quantum physics wouldn't be complete, and wave functions would kind of evaporate, remember? So again, this is allowing us to create complete spaces where the functions themselves converge. That's all we're saying. Given that this thing converges to something, right? And that's what an LP space is. If f is measurable given that it converges, all right? And this denotes that it's almost everywhere equality. It means functions are considered equal if they differ only on a set of measure 0, okay? And the norm of a function in LP space is just given by the integral of f of the magnitude of f to the p integrated over the measure to the 1 over p. All right, so that's an LP space. It's a function space. Okay. Again, let's revisit the Dirichlet function. And let's say we have a characteristic function on the interval, which tells us what? 1 on rationals, 0 on irrationals. Riemann said for any partition, every subinterval contains both rationals and irrationals, right? So if we try to partition somewhere in between this subinterval, it contains both the rationals and irrationals, so the upper sum is 1, lower sum is 0, you have no integral, okay? We're cooked. So what we got to do instead is use Lebesgue. We say, here's a set of rationals, is countable set of points, has a Lebesgue measure 0, and that's just kind of a property of Lebesgue measures, right? Because remember, let's go back to Lebesgue measures. Again, extends the notion of volume, right? So it is unique translation invariant measure, where this has to equal 1 for n, right? And so we define it in such a way for the Lebesgue measure. The countable set of points has countable sets of points have Lebesgue measure 0. All right. So for any c is greater than 0, if c is less than 1, then the set of everything, okay, the set of x, given the characteristic functions of x being greater than c, this is equal to, again, the intersection of the rationals, right, with the union, or sorry, with the interval itself, and that has measure 0. So if c is greater than 1, it's empty, and hence simple functions below have integral 1. So assuming this, right, for our Lebesgue integral, if we take the sup of that, the supremum of that, we get that the integral exists and it's 0. Okay? Because simple functions below it have integral 0. The Tame function, as well as the popcorn function, we can define it as t of x is equal to 1 over q if t is equal to p over q in lowest terms. T of x is equal to 0 if it is an irrational. So what this allows us to do is show that, yes, this is actually Riemann integrable, and because discontinuities form a set of measure 0, Lebesgue also agrees. So this is kind of like a nice consistency. Okay? Let's look at the Cantor set. The Cantor set is a subset of 0 and 1, but what it does is we remove middle thirds iteratively. So the total removed length in this case would be 1/3 k times 2 to the k minus 1, which is equal to 1. So we removed a length of 1. So thus the Lebesgue measure, again, of the Cantor set is 0. But what's funny is the cardinality of the Cantor set is a bijection with 0, 1. So that is kind of interesting. There's also something called the Vitali set, where it's also a subset of 0 and 1. But it's an equivalence class, again, under x and y, if and only if x minus y is in the rationals. So if you pick one representative for class, right, this for equivalence class, if you take the union of the intersection between the rationals from the interval of -1 to 1 over the set plus some q, right? This actually covers 0 to 2 up to boundaries and disjoint translates, because again we're going from -1 to 1, and then we just cover it from 0 to 2. So if the Lebesgue measure is greater than 0, then the Lebesgue measure from 0 to 2 is infinite. And if the Lebesgue measure of v is 0, then the Lebesgue measure of 0, 2 is 0, and we get a contradiction. So we can actually show that this set is actually non-measurable, which implies that Lebesgue measure is incomplete without the axiom of choice. But we accept completion. So this is a really fun set to play around with as well. But let's get to the main results of measure theory. Riemann integration fails, of course, to handle limits, but Lebesgue integration is great, and we get some really beautiful theorems out of Lebesgue integration. This allows for Feynman path integrals, fun fact. But if f sub n, right, let's say this is a sequence, okay, is a non-negative measurable function, okay, if they're non-negative measurable functions and sequences of n, and converge to the function pointwise, the total function pointwise, then the integrals will converge to the total integral. Okay? So in other words, if you're stacking a bunch of masses, right, the total weight is the limit of the partial weights. So in the same way, for the sequences, the total limit or the total integrals for the sequences, they converge to the final total measurable functions pointwise, then the integrals will converge. And you can prove this. And yeah, you just take the supremum over this and use the epsilon greater than 0. Okay. We can also do a valid approximation of characteristic functions. So let's say we have a sequence or a function sequence that's a sequence of chi of the characteristic function from 0 to 1 minus 1 over n. Okay. F of n increases pointwise to the characteristic function, which equals 1. And if we take the integral of the sequence to be equal to 1 over n, the limit of the integrals, 1, also equals the integral of the limit. Okay? Which is a good result. Okay? And let's look at the non-negative measurable sequence f. This is always going to be less than or equal to, right? If you take the limit of the infinitum of the sequence, right? And we take the integral of it. This is less than or equal to the limit of the infinitum of the actual integral itself. And this is Fauteuil's lemma. So all we have to do, again, the quality of this is not guaranteed because mass can escape to infinity or vanish into a thin spike, right? Because of the measurable outcomes, right? There's leakage over the integrals. But what we can do is construct a sequence that shows us that it does converge, or it's less than, right? It gives you the inequality. And the monotone convergence, if we apply this, then we can have that the integral of the sequence is less than the integral of f of n for all n is greater than k, right? So that's a good one. And then we take k to equal to go to infinity. If you look at the strict inequality for this, the sequence can be equal to n times the characteristic function on the interval. And if you take a pointwise limit to be 0, then the integral of 0 is equal to 0. But the integral of the sequence is equal to 1. So 0 is less than 1. And this gives you a nice strict inequality for the characteristic functions that can be used later. And guess what? This will allow us to move on to the dominated convergence theorem, okay? So remember, we have the monotone convergence theorem, we have Fauteuil's lemma, and basically this is a very important result because if the sequence converges to f almost everywhere, then there exists a roof function, g, in L1 such that the size of the sequence is less than or equal to g, less than or equal to g for all n, okay, of that roof function, okay, that just there exists, okay. So again, as we integrate and it converges to f, and the distance between f and the sequence itself will tend to 0. And the proof is a little bit involved, but you can, again, use Fauteuil's lemma here and show, again, the limit of the infinitum, is interchangeable with 2 times the integral of g minus the limit of the supremum of the integral of this difference, okay? which then implies that the limit of the supremum of the difference here is less than or equal to 0, which implies that it's equal to 0. So we can then have this nice form for the dominated convergence theorem. Okay. Another thing is to check out is the sequences or the function of x that depends on power, or there are power functions on the interval from 0 to 1. So if the sequence tends to 0, except of course that x equals 1, it's dominated by g of x, again, g of x is equal to 1, which is a finite integral 1. Then the conclusion is that if we integrate the power functions and substitute in, that the integral is 0, we can check again that this converges to 0. So we can conclude that a point mass at 1 has measure 0. Next is product spaces and completeness. So these are really some of the workhorses of measure theory that you didn't even know came from measure theory, which are Fubini and Tonelli's theorem. Okay, and you definitely use this if you've ever done some calculus 3. When can we swap integrals? And we can really only know this with the power of Lebesgue integration, because for a scalar, or sorry, for a function that depends on x and y, again on Rn across Rk, if the function is positive or equal to 0, we can always swap the order, and it might be infinity, but that's okay. Okay, but Fubini says if the integral is finite, then the order doesn't matter, and the integral is finite. So essentially, you can prove this with like iterated characteristic functions. But an important consequence of this is the Gaussian. It allows us to say, well, if we want to compute e to the minus x dx from negative infinity to positive infinity, we can just square it, right? We can square it into a double integral. And if we choose to square it, then if we're allowed by Fubini's theorem, right, because it's finite, to just switch it to polar coordinates and just compute that that this integral here is equal to pi, and just take the square root of it. So that's great, because it says again the order doesn't matter, the integral is finite, whatever. That's Fubini's theorem. So yeah, good stuff. And then the last thing, and this is probably the most important result for quantum mechanics, is the Risch-Fischer theorem, which says that if we have LP of a measure, right, if we have a function space of measure here, it's said to be a complete Banach space for 1 is less than p, less than or equal to p, which is less than or equal to infinity, or it's just finite, right? Well, L2 of a measure is said to be a Hilbert space. And why this is significant is because it provides a home for quantum mechanics. And a Cauchy sequence then of wave functions it converges to a valid wave function inside the space. So we can prove this again for p is equal to 2. Take the Cauchy sequence of f1, right? And let's assume it's a wave function or something. Well, technically it wouldn't be, but it's okay. The subsequence of n sub k with a norm, if we take the difference between the subsequence f sub nk, and where p is equal to 2, this is less than or equal to 2 to the minus k from our earlier definition, definition of LP spaces. Okay, and we can show that this is finite, and by using the monotone convergence, we can then have that this subsequence converges absolutely to some f of x. And it's dominated, again, dominated convergence theorem by L2, which implies that f is in L2, the function space. And so the subsequence that tends to f is also in the function space, and hence the original sequence also converges. This is huge. because now we have constructed officially the Hilbert space in terms of Lebesgue integration, or Lebesgue integrability, all right? The last theorem that we're going to talk about in measure theory is honestly probably the most important theory, or the most important theorem, and most consequential one, because it allows us to differentiate measures themselves, okay? So if a measure if a measure nu is absolutely continuous with respect to with respect to mu, mu of a is equal to 0. If we have that the measure of the measurable outcomes, the set of measurable outcomes is equal to 0, this implies then that a measure nu of a is equal to 0. And if mu is sigma finite, then nu is just the integral of some density function h. So we can actually just integrate, we can find the new measure, or I guess it is technically a new measure, but like a new measure of the possible measurable outcomes by integrating over all the measurable outcomes for some density function h, the integral of that with respect to the other measure. So we can generalize the concept of density functions and Jacobians, and that's what we have here. So h is the density, and we can just interchange between measures. So what's really, really profound about this is, or you can first prove this by constructing h by exhaustion of derivatives on sets, because that's essentially how we would define the density, right? But we now have an integration theory that completes Hilbert spaces, justifies everything, and we can interchange limits and integrals and quantum mechanics, and that's why path integrals are allowed to work. And so, long live Lebesgue, This is the only integration theory that's incompatible with modern physics, because we can define the integration in terms of measure and LP integrability spaces, okay? So now this is probably the most satisfying culmination of our analysis, because we have finished analyzing the continuum, okay? But now we're going to show that this special case, and there's a very interesting special case of Lebesgue theory, or measure-theoretic probability, where we define that uncertainty is really just normalized measure. And we can now define stochastic processes, okay? So now that we have completed the analytical continuum, limits, derivative integrals over pathological sets, convergence theorems, topologies, we have everything under control, right? We really, the final, I guess, revelation is that, for centuries, probability theory was just a mess of paradoxes and gambling intuition, and nobody really knew what chance was or odds. And it wasn't until 1933 that Kolmogorov, a Soviet mathematician, realized something shocking, is that probability isn't a separate field of math. It's actually a special case of the Lebesgue integration we just built. And it's really subtle, but if you frame it in such a way, and you think about it in such a way, we can really banish this philosophical vagueness about equally likely outcomes and replace it with something rigorous, okay? So what this looks like, Kolmogorov came up with 6 axioms, and you can look at them. But basically, he resolved a lot of the paradoxes that, uncertainty isn't some mystical kind of thing. It's integration with normalized measure. And this really shifts vagueness to mathematical rigor, that allows us to have intuitive notions with precise definitions that have been established in measure theory. So, really, when we say a sample space, well, we mean the set of all possible outcomes, okay, analogous to X. And, when we say an event, we mean a measurable set, right? That's the event. That's an event, or a sigma algebra on omega, which would be the event space from the sample space. And a random variable is just a measurable function. So, an expectation would be what? That would be a Lebesgue integral. Okay, so this is great. So now that we have a random variable and it's a measurable function, we can map the probability, the sample space in the event space, or the sigma algebra, to the real numbers in the Borel sigma algebra, or the real numbers. And what that means is we map abstract outcomes to real numbers in a way that preserves structure. So we define the distribution of X as the push-forward measure on R. All right? And the expectation, so let's say we have X as a random variable, its expectation is the Lebesgue integral over the sample space. All right? Integrated integrated on the set of possible outcomes over the probability measure. Okay? So let's say we have events and they're all independent. If we take the intersection of all the events, or the probability measure of the intersection of all the events, to be equal to the product of the probability of those particular events. All right? Now, sigma algebras, let's say F1 to Fn, these are independent if any choice of events are within those particular sigma algebras, and they yield independent events. Now, here's where the hardest concept is really made simple in measure theory. It's the idea of conditional expectation. So, what is the expectation value of, seeing this particular event given some sub-sigma algebra? So let's say we have some partial information, right, where we have a sub-sigma algebra of our original event space. The conditional expectation, then, is just the best guess of X using only information in G. And what that looks like, then, is the expectation of X given G is unique, almost surely, okay, AS, almost surely, if G measurable random variable Y, such that for all events, right, in this sub-sigma algebra, if we were to integrate, the random variable Y and X over the same probability measure of the same samples or the same space of possible outcomes, that they're equal to each other. Okay, both of those integrals must be equal to each other, and this is guaranteed by, guess what? The Redon negative theorem. So Y is essentially the density. Y will become the density of the measure X dp. Okay, with respect to P restricted to the sub-sigma algebra. In geometry, then, what this really looks like is that the Hilbert space, in a Hilbert space, this is the orthogonal projection of X onto the subspace of G measurable functions. Doesn't that just complete everything? It completes the entirety of the continuum that we're trying to analyze and construct. And really, truthfully, this probability and the its inheritance of the mechanics of Lebesgue theory is just incredible. So what we can do now is say, well, filtrations and martingales. Let's talk about filtrations and martingales. So a filtration is that if we have a sigma algebra that depends on time, right, where time is greater than 0, and we have an increasing family of sigma algebras. So this means that we can see information accumulating over time. We can say a process is said to be adapted if the set of outcomes over time is f sub t measurable for each time. So for each instance of time, it's measurable. Okay, the event space is properly calibrated. The process then, x of t, can also be said to be a martingale if the expectation value of the magnitude of the process is finite, okay? And if we say that the expectation value of x of s, okay, where x is sometime, after t, okay, so we want the expectation sometime after the time, the current time. If the expectation value is equal to x of t, surely for all times after t. What that means, okay, what that literally means is we're talking about, again, projections in a function space. So given everything I know about the filtration, my expected future value is exactly my current value. We call that a fair game. All right? Because if we keep rolling the dice, right, we know that the sigma, or the measurable, the information accumulating over time, right? We know it's not really going to change much, right? So we keep rolling the dice and we know exactly how the event space is evolving through time. It's not changing at all, right? That would be a fair game. All right. Now let's look at the continuum. So let's say we have a continuous probability space from 0 to 1. The filtration here is the Lebesgue measurable sets, and we could just have the Lebesgue measure for our probability measure. And let's say the variable is just, x of w or of omega, and the expectation would be the integral from 0 to 1 of omega, which is 1/2. Okay, so that's how we would, calculate an expectation value for a continuum. For a dice roll, let's say we have these discrete probabilities, and again, we can use the measure. So let's say it's a uniform measure, so it would be 1/6. And the variable would just be then the identity. So we can then get that the expectation value of the dice roll is 3.5. All right. And let's look at the martingale. So again, that's a fair game, right? Let's describe something called a simple random walk, where we have a probability of incrementing +1 or -1 at n plus 1. All right, so recursively defining this game, or this fair game, right? Well, the expectation value of x of n plus 1, given some sigma algebra of n, right, is equal to 1/2 with x plus 1 and then 1/2 x minus 1. Guess what? We just return, again, we know it's a martingale. It has to be a martingale because we know exactly the probability or how the filtration is changing. So there's nothing crazy about that. All right. Now, let's look at some of the theorems of probability given our measure-theoretic background now. Looking at the dominant convergence theorem for expectations, if we have, some outcomes, right, x of n to converge to x almost surely, then we know that x of n is less than the y random variable with a finite expectation for y. Okay, if we know both of these things, then the expectation value for x is going to converge to the expectation value for x, okay, or x sub n. It will converge to essentially allow us to approximate complex systems with similar models, okay? And here is the Bernoulli trial, which shows, the strong law below, and that the expectation value of z of n for the setup of, hey, we have the sum over n minus the probability, the sum sub n is equal to just the sum of all the possible outcomes, okay? And we're defining z in this way. The expectation value would be 0, of course, for Bernoulli trials, right? With some probability and another 0 with another probability of 1 minus p, right? So Another theorem that we can look at is the strong law of large numbers. Okay, this is from Kolmogorov in 1933. So he said for independently and identically distributed variables, x sub I with finite mean mu, we can say that this the sum, again, the sum of this is just or the sum of the set of all the variable or of all the possible outcomes would just then be a sum over everything divided by the sample or the sample space or essentially what this allows us to do is to say that it converges to the mean, right? So the average really will actually converge to the expectation with probability 1, and this allows us then to connect experiment or empirical reality with theory and limits in mathematics, okay? Mathematical limits. If we assume that E, or the expectation value of x to the 1 is equal to 0 at the center, you can also use Kolmogorov techniques as well to show truncation error tends to 0. So that's exactly how you would prove this. For coin flips, probability is 1/2. Proportion of heads tends to 1/2. Okay, that's a really basic application of this, but it can't get much harder than this. The central limit theorem. So if we look at Lindbergh-Levy for independently and identically distributed variables, if you have a mean mu and a variance sigma squared, take the sum of all the outcomes, subtract off by the number of trials. Okay, I like the Bernoulli trials. But we're multiplying it by mu and then taking the square root of n times the variance. This will imply a normal distribution, okay, 0, 0,1 parameters, right? So with a mean of 0 and a variance of 1, all right? So what we can do to prove this is use characteristic functions, which are the expectation value of e to the minus it, and essentially that's kind of like a Fourier transform. And if you do Taylor expansion of the characteristic functions, this gives you the normal distribution. Okay, so the central limit theorem is essentially this. All right, and you can prove this by just characteristic functions as well, and something called the Levy continuity theorem. All right, another thing you can do is Dub's martingale convergence theorem, which allows us basically to say that if a martingale process, right, is bounded in an L1 space, then we can take that the supremum of the expectation value is finite. Then x sub n converges to some random variable almost surely in that function space. So what that means is that equilibrium states can be reached in closed systems. And really, these kinds of law of large numbers, the Doob martingale convergence theorems, were really stating, convergence theorems for about function spaces, right? And you would prove this just by showing that inequality bounds oscillations, and then with convergence in L1 by dominated, uniform integrability from the bounded definition, right? In terms of the Lebesgue integrability for P is equal to 1, all right? And its finiteness. Okay, next, you can talk about Brownian on branching processes as well. Another thing, this is a very important result to show that variance is non-negative, is something called the conditional Jensen's equality. And all you have to know is that if a function is convex, then the expectation value, if the function is convex, then if you put the expectation value of the filtration, right? Oh, sorry, expectation value of the random variable given some sigma algebra, this will be less than or equal to the expectation value of the function of the random variable, of the convex function of the random variable, given the same sigma algebra. Okay. And you can apply this then to expectation value of, x squared minus the square of the expectation value of x is greater than or equal to 0. All right? And you can prove this on the probability space for all possible outcomes and the probability measure for each probability outcome. Okay? And the last thing that we can do is look at the variance, which basically allows us to employ this inequality. So, yeah. And again, it's just expectation value of x squared, of the random variable squared, minus the square of the expectation value of the random variable. That's the variance. Okay. Now we're going to culminate the entirety of continuum analysis by constructing the fundamental object of stochastic analysis. So the first thing that we do is, with this theorem, we want to show that Brownian motion exists, okay, in the continuum. We would say there exists a process, b of t, for t is greater than 0, on some probability space, such that b of 0 is equal to 0. T maps, so as t will map to the process continuously, almost surely. And 3 is that it has independent increments, okay? And 4, the Brownian process at t, and then for t, or for some s less than t, if we take the difference between that, it is distributed accordingly to a normal distribution for t minus s, as s is less than t. Okay, this is the formal Brownian motion process. And you can prove this with Kolmogorov's extension theorem, and by finite dimensional distributions, so the Gaussian, consistent covariance. They're also, then separability and continuity, we can prove this, okay? So, this is one of the coolest things ever, and probably one of the coolest fields of math, as stochastics. And the reason why is because if we want to take the variation, right, or if we want to take, you can think about this in terms of, like, what is an infinitesimal, right? And the infinitesimal would be really would be a number that's kind of small, almost 0, but it's not quite, right? Or we defined it in terms of the inequality. Well, guess what? The infinitesimal has variance, and that variance is literally time. So if you take the sum, right, where t greater than 1 minus t for these particular subsequences of the Brownian motion, and we want to square that difference, the square of that difference between them, or the square of that sum between them, is equal to, it converges, the variance of it converges to time along these dyadics, okay? The last thing that we'll cover is Levy characterization. And this basically means that for any continuous martingale in sub t, with m0 is equal to 0 initially, and quadratic variation, okay, where it depends on time, any of them is a standard Brownian motion. So this gives us, again, on the continuum, as we have analyzed the continuum from, basic, calculus to topological spaces, and generalize those to, multivariable and complex analysis spaces, and then we need to redefine integrability and then probability. What now we have, truthfully, have arrived at is that Brownian motion itself is universal, something that is deeply physically observed by Robert Brown, who's actually a biologist. And notice that the mean of, or the variation of the particles as they move through time tends to be random and had a Brownian type distribution, normal type distribution for their displacement continuously through time. And the mathematics has led exactly to this moment. So just as the central limit theorem, right, says everything sums to Gaussian, Levi's theorem says every continuous fair game with constant volatility is Brownian. So you now can see that really we have unified the system. From some static number line, we have built limits, and from limits, we have built derivatives, linear maps, and we found the rigidity of the complex plane. We fixed integration by measuring sets, and finally, we have realized that uncertainty itself is another form of integration. So we have built the stage, the machine is ready, and now we can truly start trying to describe the physics of the universe. But of course, we still have to build the mathematical tools to do this. But we have arrived at a very interesting point where expectations, martingales, Brownian motion, stochastic integrals, quantum states, they're all special cases of the machinery we now possess. Thank you for watching.